Okay, this is the first example for our review with the solutions to some of the quiz questions. So here it asks us to draw a direction field for this differential equation. We're going to draw the direction field last and include a plot of a solution where we have some different initial values. Okay, let's start by writing out the differential equation and setting things up so that we can solve this using integrating factors. We're told that this has a value for t that's greater than 0, and for our purposes later, we're going to set up an initial condition of this, and we're just going to use a placeholder value here. And this placeholder value will let us be able to make a Desmos plot to where we can change what the initial value is of the equation. Okay, so we want to set up the method of integrating factors. In order to do that, we need to divide everything by t here. This gives us an expression that we can apply our technique to. We see that the function for p is going to be negative 1 over t. And so we are going to take the exponential of the integral of that function. And so we're going to get exp of negative ln t. We can drop the absolute value on the natural logarithm because we're told that t is positive. And so altogether, what we're going to get here is one over t. The reason that that works is because we're going to get e to the ln t, and we can take a product of exponents as a power to a power. Okay. With our integrating factor, our left-hand side is going to be the derivative of the product of our integrating factor and y, and then we multiply the other side by the integrating factor to just get e to the minus t. We integrate both sides. We're going to get 1 over t times y is equal to negative e to the negative t plus the constant of integration, and then we get y by itself by multiplying everything by t. So we're going to get c times t minus te to the negative t. Okay, this is our general solution. And now what we can do is apply our initial condition by plugging in 1. We have to choose a t not equal to 0 because we're given a positive value for t, which is why we're applying our initial condition here. Have some placeholder value, why not? That's going to be equal to c times 1 plus, or sorry, minus 1 e to the negative 1. And so y naught is going to be equal to c minus 1 over e. And this implies that c should be equal to y naught plus 1 over e. And so our solution to the initial value problem looks like this. All right, now this is something that we can plot in a direction field and see how this all works. Okay, so transitioning to this direction field plot that I have made. We can see the direction field with our differential equation in the rewritten form that we use to solve. And here we have a value for a, which is the value that I called y naught, which is the y value that we pass through. And I've also plotted the point 1a so that we can verify that our solution function here, which is written in terms of the initial value with our condition that our input be greater than 0, adjust appropriately, and we can see the solution to the initial value problem change as we manipulate that condition here. And so as we are close to a 0 here, we get kind of the most interesting curve of the function with the most pronounced features. And then as we get away from 0, the function grows very quickly in one direction or the other, and we can't really see many extra details there. All right. So this is one example here, utilization of integrating factors and the consequences of solving the initial value problem. Next up, we have a separable equation. So if we write this out, y prime equals 2x over 1 plus 2y. The main thing to notice about this expression is that it can be rewritten in this form, which is noteworthy because we have separated everything that depends on y from everything that depends on x. And so if we wanted to, we could write these as functions here. Okay. It's also pretty common to see this written like so, where we have y prime written as dy dx, and to split the parts of that differential to separate sides of the equation. And writing the integral like so in order to do the evaluation step. Okay. I don't have a strong preference as to which way to write it. I think that this notation personally is a little bit misleading, even though a lot of people like it because it keeps the letters and variables collected in an interesting way that keeps things easy to keep track of. However, the thing to note here is that this line is extremely important, and what it's actually telling us is that we are, even if we write this, really differentiating both sides with respect to x. It's just that that differentiation with respect to x is kind of hidden in the way that we write the expression. For practical purposes, however, we are on the left integrating by y and on the right integrating by x. So writing down that computation, we're going to get y plus y squared equals x squared plus a constant of integration. And what we can do for this expression, because this is easy enough for us to be able to ultimately write this as a function of y, we'll go ahead and write out things like so, setting up a completion of the square. So we take half of the coefficient on y and square it, which is where the 1/4 comes from, add that to both sides. And now what we can do is write the left-hand side as the quantity y plus 1/2 squared, and on the right-hand side we're going to have x squared plus a constant c. I have decided to absorb the 1/4 into our constant integration because when we solve the initial value problem, that will work itself out. Okay. Now we can take the square root of both sides. This is going to give us a plus or minus term in front of the radical. And then lastly, we can subtract 1/2 from both sides to get our general solution to the problem. Now that we have our general solution, we can apply our initial condition. which says that at 2, our function's equal to 0. So we plug that into our function. We want to work this out as far as we can, so we're going to get -1/2 plus or minus the square root of 4 plus c. We're going to add 1/2 to both sides. That's going to make us need to choose the positive square root in order for our initial condition to make sense, leaving us with the square root of 4 plus c on the right hand side. And so we square both sides and subtract 4. It's going to equal to c, so we're going to get -15/4. And we'll write our solution to the initial value problem in a different color here. It's going to be y equals -1/2 plus the square root of x squared minus 15/4. We're asked to determine when our solution is defined. The obvious restriction to the domain here is that we require that our radicand to be positive. So that means that we require that x is going to be greater than the square root of 15/2. And if we switch over to a graph of our solution, we can see that that is approximately what's going on. We have a value that is slightly smaller than 2 as the origin of our graph. The square root of 15 over 2, because the square root of 16 would be 4, so we get 4/2, which is 2, so the number is slightly smaller. And otherwise, there is no restriction to our graph, and we see that we have this nice plot here. For this problem, we're going to be looking at an autonomous equation. We recognize that it is autonomous because there are 0 occurrences of the independent variable on the right-hand side here. And so where we want to begin is by looking at a small sketch of f of y, which is y prime, versus y here. And so looking at our function, we can see that this is going to be equal to 0 whenever y is equal to plus or minus 1, as well as when y is equal to 0. So we're going to have -1, 0, and 1 all be relevant here. So we'll sketch our graph. And if I want to figure out how this thing looks, what we can do is we can plug in, say, -1/2 into this expression. If I plug in -1/2, I'm going to get positive 1/4, and 1 minus 1/4 is going to give us 3/4, which is a positive number. And then y is going to be negative. So a positive number, negative number is going to give us negative value. And then we can do the same thing by plugging in 1/2. We're going to get a positive value in that case. So we expect this to look something like this. And we know that the end behavior is going to point in different directions because this is a cubic polynomial if we multiply everything out. Okay, so this gives us a small sketch here. The main points of this plot are that in this region, the solution should be increasing. In this region, the solution should be decreasing. In this region, the solution should be increasing. And in this, decreasing. Okay. What this allows us to do is create our plot for the phase line. And so if we have here 0, and -1, and 1, which are our equilibrium solutions. Then we increase down here, decrease down here, increase here, and decrease here. We can now make our plot. Put in our equilibrium solutions. And plot our lines here. Now, one of the things that we may be concerned about for graphs of this type is when we're going to have our inflection points. If we wanted to plot those inflection points, we need to go ahead and figure out when the derivative of this is equal to 0. So in order to do that, we say that y prime is equal to this. And we are interested in finding y double prime equal to 0. So we differentiate with respect to y. And so the easiest way to do this is actually the product rule. So we'll take the derivative of the first function, leave the second function alone, and then take the derivative of the second function, leaving the first function alone. Want this to be equal to 0. We're going to get 1 minus y squared minus 2y squared. And so we're going to get 1 equals 3y squared. And so if we solve for y, we're going to get plus or minus 1/9. And so that tells us that our inflection points are pretty close to 0. So they're going to look something like this. And for the rest of the behavior of our graph, we can rely on our function here. So we use our phase lines. These are all going to look like this, asymptotically approaching the equilibrium solution. These down here are going to asymptotically approach like this. These that start up here are going to change concavity. They're kind of hard to draw because we have to sneak them in there, but that is how they behave. So they'll be concave up, then concave down, and do this. And then these are just going to be concave down the whole time. And likewise for solutions that come from above here. All right. So this is what our qualitative analysis for our solutions look like, and we can, based on this information, note that this is a stable equilibrium point, this is unstable, and this down here is stable. All right, so that's how to completely solve one of these problems. No calculators needed for graphing utilities or anything like that. All right, in this question, we're going to be examining this differential equation and determining the value of b for which this is an exact equation. So let's copy it down here. Okay. Now the idea behind this is that it is, as an exact equation, tied to the idea of potential energy. And so when you take calculus 3, what you'll find is you'll have some function of multiple variables here, x and y, and you'll take the gradient of that function, and the idea would be that the first of these would be the derivative of this function f with respect to x, and the second would be the derivative with respect to y. And what you want to have happen here is for this, if we take the other partial derivative, for everything to end up matching. So our condition is going to be related to these partial derivatives. So what we want to do is look at the partial derivative here. We're going to be differentiating with respect to y because we already should have differentiated with respect to x for the gradient. So we're going to get 2xy plus b times x squared. And then for the other term, we want to take this partial with respect to x. And we'll go ahead and multiply through by the x just so it's easier to see that we're differentiating a polynomial here. And we're going to get 3x squared plus 2xy. We can see pretty clearly here that taking these two things together, we must have b is equal to 3 in order to satisfy the condition of this being an exact equation. So we can now rewrite the original differential equation with this in place. And we want to solve our exact equation here. Okay, so we're looking for our potential function f, and it is going to be the integral with respect to the appropriate variable of one of these two functions. Let's go ahead and integrate with respect to x, this first function here. And so we're going to get 1/2 x squared y squared plus, forgot a square here when I copied this down. This is going to be x cubed y, and then plus some function that depends only upon the other variable y here. Okay? If I take this and take its partial derivative with respect to y, then it will have to be equal to this function here. And so let's compute that, see what it looks like. If we differentiate with respect to y, reduce the power, we'll bring the power out front, and then reduce the power by 1, so the 2 times 1/2 divides out. And then we're left with plus x cubed here, and then plus g prime of y, and this has to be equal to this expression. We see that these two terms match up, so that implies that g prime is 0, so g of y is just some constant, and we're allowed to write down that our potential function as a function of x and y is equal to 1/2 x squared y squared plus x cubed y plus a constant. And of course, as you know, we generally set this up so that we set this whole thing as equal to a constant, so we'd write it like that. All right, so pretty straightforward exact equation. Most important thing to do at the beginning of the exercise is to check to make sure that the exact condition is appropriately satisfied, and then follow along with the method as outlined. Okay, here we have a question where we're just looking to find the general solution of a second order linear equation with constant coefficients. This is a homogeneous case, so our solution is very straightforward. All we're going to do is, under the assumption that our solution has the form y equals e to the RT, plug this in, use the characteristic equation, find the roots, and then find the form of our solution. So the characteristic equation is something that we can write down right away. The power of r is equal to the number of derivatives that appear in our term, and this is something that we're going to be looking to factor if possible. We can factor this expression into r plus 3 times r plus 4. 3 plus 4 is 7, and 3 times 4 is 12, so that all works out. What this tells us is that r is equal to -3 and -4. So the fundamental solution for this differential equation is going to have a form y equals c1 e to the -3t plus c2 e to the -4t. And in this case, that's all there is to it. All right, here is an initial value problem to solve. We're still working with homogeneous equations, so all we need to do is find the fundamental solutions and then apply our initial conditions. We can, again, go straight down to writing our characteristic equation. Okay, looks like this, and there are a couple different ways to handle this. If you don't recognize immediately that this is factorable, we can, of course, use the quadratic equation and go with -b plus or minus the square root of b squared minus 4ac. This is going to be all over 2a. This is going to give us 5/4 plus or minus the square root of 49, which is 7, and then over 4 here. And this is going to simplify to if we're adding 3 and if we end up subtracting -1/2. Okay. You also could have noticed that this expression here factors like so. 2r times r is r squared. 1 times r is 1 factor of r, and then you get -6 factors of r, so that's where you get the -5r, and then lastly -3 times 1. Either way, we get that our general solution is going to be equal to c1 e to the -1/2 t plus c2 e to the 3t. It doesn't matter which one's y1 and y2. And then so we have this expression now. We're going to want to go ahead and differentiate this in order to be able to figure out what's going on with our coefficients to apply the initial conditions. All right. So in the setup, what this allows us to do now is set up a matrix equation where we're going to have 1 and 1 and -1/2 and a 3, c1 and c2, and this right hand side is going to be equal to -3 and 1. I didn't explicitly write out plugging in 0 to our equations here, but of course if I just plug in 0, these both go to 1, and these both go to 1, so it's really easy to see without working it directly how that looks. However, if you have an initial condition that's not evaluated at t equals 0 or some other value, you need to be a little bit more careful about this. Just do the little bit of extra work of plugging it in and writing down what you need. But the idea is that you want a linear combination of C1 and C2 equals a number, and a linear combination of C1 and C2 equals another number to set up the matrix equation. With the matrix equation, we can write down Kramer's rule for this expression here. All right, and so we want to work all this out. In the denominator, we're going to get 1 times 3, which is 3, minus negative 1 times negative 1/2. So this is going to give us 7/2. And then in the numerator, we're going to end up with a negative 9 minus 1. And we can simplify this to negative 20/7. For C2, it's a similar process. We just replace the other column this time. And we've already computed this denominator, so there's no need to repeat that calculation. So we're going to get 1 and then 3 negative signs. So it's 1 minus 3/2, so we're going to get negative 1/2. And so this simplifies to negative 1/7. Putting everything together, we can write down that our general solution is negative 27 e to the negative 1/2 t minus 1/7 e to the 3t. All right. Switching over to a graphing utility, we can see that this is what the plot of the solution looks like. And to take things a step further, let's go ahead and take a look at what's going on with our initial conditions. We know that our function has a slope of 1, and also that the line passes through negative 3. And so if we actually plot that line on our figure, we see that the value of the function and the derivative matches those values. And so when we apply initial conditions, this is what we're doing. For second order equations, we have a position and a velocity, effectively, thinking about that in terms of the first derivative and second derivative, or excuse me, the value of the function and the first derivative. And the differential equation tells us what the behavior of the second derivative is. And so if we have a higher order differential equation, we have more initial conditions that need to be satisfied. For instance, a third order equation that has a third derivative, we would have a parabola or a quadratic function whose graph would be tangents, and all of those derivatives would align at the place where the initial condition is being applied. So this is a bit of a preview of some stuff we're going to see in Chapter 5, but this idea ties into what it means to assign initial value. Okay? But this here is our function. It obeys our initial condition and is what we get as a result of solving this differential equation. All right. In this question, we're being asked to find the general solution to a non-homogeneous equation. And for this, based on the right-hand side, we should be able to use the method of undetermined coefficients. We're going to begin by solving the homogeneous equation. We'll begin by writing down our characteristic equation for the homogeneous case and seeing that this factors our roots are repeated roots are equal to -5. This suggests to us that the homogeneous solution should be of the form c1 e to the negative 5t plus c2t e to the negative 5t, because we need linearly independent solutions here. Okay. Looking at this, one of the things that we'll notice is that one of our functions on the right hand side is linearly dependent upon our fundamental solution, and if I increase the power of t here for my guess, it will still be linearly dependent. So what I'm going to need to do is guess a function that has one more power of t, so it'll be t squared e to the negative 5t for that function. Okay. So we're going to have two components for our particular solution. We'll go ahead and compute them independently so things are easy to keep track of, and we can keep our guesses and derivative computations simple. So we'll use capital Y sub 1 for our first particular solution part, which will correspond to t e to the t. And based on the discussion we just had, we'll use b t squared e to the negative 5t for our other guess. Okay. Linearity says that we can compute these independently, so we're going to do it this way just to keep things as simple as possible. And that's particularly important because we start getting product rule derivatives for this other factor here. All right, got a little bit cramped there at the end. That's all right. Slide this over here. Okay, so there are our two sets of derivatives. We can plug those into our equation, and after plugging them in, figure out what each component of our particular solution is going to be. So we have a e to the t plus 10 times a e to the t plus 25 times a e to the t. And this is all going to be equal to 2 e to the t. So putting everything together here, we're going to have 36 factors of e to the t on the left and just the 2 on the right. So a is going to be 1/18. On the other side, we have this somewhat complicated expression, but it simplifies a little bit. So that's going to be the second component of our particular solution. And so plugging everything in, we're just going to have a b on the outside of everything. So we'll leave that factored out. 25 t squared e to the negative 5t minus 20t e to the negative 5t plus 2e to the negative 5t, and then times 10b 2t e to the negative 5t minus 5t squared e to the negative 5t, and then lastly plus 25b times t squared e to the negative 5t, and this is all equal to 2e to the negative 5t. All right. Now, looking at how all this shapes up, ten times this is going to get rid of all of those. And these are going to add out, which is just going to leave two b e to the negative 5t is equal to 2e to the negative 5t. Therefore, b is equal to 1, and we can write out our full solution. Starting with the fundamental solution to the homogeneous equation. And finished off with our two components for the particular solution. All right. For this problem, we're going to be solving a non-homogeneous equation, and we are going to need to use variation of parameters. We want to write down our characteristic equation for the homogeneous case, and I do want to take a second to point out that it is extremely important that you pay attention to the form of the solution here. It's a very common mistake on these types of problems for people to write down the wrong characteristic equation, because for some reason they see a prime here that's not written down, and on variation of parameters problems in particular, that's going to make things miserable to compute, because your particular solutions aren't going to be reasonable. Okay, so please don't make this mistake. It is very common, more common than you would think. So please, the power on R is the number of primes. Don't forget that. Okay. For this, we see that we're going to have complex valued roots for R. We're going to get R equals plus or minus 3i, because we're going to have the square root of negative 9. This tells us that our homogeneous solution is going to take the form of cosine and sine of 3t. And with the sine and cosine here, we can now set up to be able to find our particular solution. The derivative here, of course, is very easy to compute. And we set that up so that we can know what our matrix equation is going to look like. We're going to have cosine 3t and sine 3t. And then down here, we're going to have negative 3 sine 3t and 3 cosine 3t. We're going to have u and v here, and this is going to be equal to 0 and 9 secant squared 3t. Okay. This, of course, is all based on the fact that we are assuming that our particular solution can be written like so. So we'll return to that after we have figured out what u and v are. Sorry, I forgot my primes here for u and v. But now we solve this matrix equation, looking for u prime. We'll set up Cramer's rule. Secant squared 3t here, and then sine of 3t and a 3 cosine 3t. Let's go ahead and do the Wronskian here on the side so it's not on our way. So we're computing the determinant of this matrix. We're going to get 3 times cosine squared minus negative 3 times sine squared. And so what this is going to look like is 3 times cosine squared of 3t plus sine squared 3t after factoring out that 3, so the Wronskian is just 3. Computing u prime, we take 0 times 3 cosine 3t minus 3t times 9 times secant squared 3t. So we're going to get 9 sine 3t times secant squared of 3t all over 3. We want to simplify this. We're going to get negative 3. Left over in the numerator, we're going to have sine 3t here divided by cosine squared of 3t using the reciprocal identity for secant. And so this is going to end up looking like secant times tangent would be one of the ways that we can think about this, thinking about it as sine over cosine times 1 over cosine. So negative 3 secant 3t tangent 3t, which we're happy about because that is a function whose antiderivative we're familiar with. Next up, we write down v. So we're going to look at v prime. We want to find it. We're going to have a 0 and a 9 secant squared of 3t here. And then in the left-hand column, cosine of 3t, negative 3 sine of 3t. And then in the denominator, we'll just have a 3 here from the Wronskian. And this is going to give us 9 cosine of 3t secant squared of 3t all over 3. cosine and secant are, of course, reciprocals of one another. So we'll lose a factor of both, and we're left with 3 times secant 3t for v prime. These are both pretty straightforward integrals. Just trig antiderivative identities. For secant times tangent, the antiderivative is secant. And we're just going to get negative secant here because we substitute u equals 3t. That substitution will give us a 3 in the denominator, which will divide out with the negative 3 that we have. So we just have this plus a constant. And our condition here, restricting our domain from 0 to pi over 6, means that we don't have to worry about any absolute value stuff. We're definitely going to be in the first quadrant, and all of our functions that we're going to interact with are invertible and positive. V is next. We write down 3 secant 3t dt. This is another formula that you should be familiar with. Maybe it's a little bit less likely that you remember this one, but it is a common one. We have the natural log of secant 3t plus tangent 3t. Again, with the factor of 3 being taken care of by the substitution that we make for integrating the 3t part. We're going to have a C2 here, and again, we don't need absolute values for our logarithm, even though traditionally they should be there because of that domain restriction I just mentioned. We have all of our pieces now, so we can write out our full solution. We have our solution in this form: y equals u times cosine 3t plus v times sine 3t. We substitute in our functions. We're going to have negative secant 3t plus c1 cosine 3t plus the natural log of secant 3t plus tangent 3t plus another constant, sine 3t. We collect our homogeneous solution out front just for neatness. Secant times cosine, because they share the same argument, is going to be equal to 1. And so we'll have negative 1 here. And then lastly, we have our natural log times sine of 3t. There's a couple different ways to write this. You can write the sign in front so that there's no ambiguity about what belongs in the argument of the logarithm or not. Parentheses would also be fine. All right. So there is our full particular solution for this differential equation.